Hello and welcome back. It's time for a quick introduction to PCA, just some definitions to start with. First of all, eigenvectors of the covariance or correlation matrices are orthogonal, just because these matrices are symmetric. The eigenvectors, as always, are ordered by the magnitude of their eigenvalues. Eigenvectors are assumed to be unit vectors, expressing only a direction. And I'll give more detail on this later, but for the covariance matrix, we want to think of our data as being centered to begin with. And that just means that the average vector, or the mean, has been subtracted from all of the data points so that the directions that we draw are drawn from the origin, which represents the mean. And this will be true of all the plots that I show you on slides. For the correlation matrix, which we're not going to get to today, but we want to think of our data as standardized to begin with, which just means that not only has it been centered to have mean 0, but it's also been divided by its standard deviation. The first eigenvector of either of these matrices points in the direction of maximum variance in the data. That eigenvector is the first principal component. Now, I say the direction of maximal variance, which would be that dotted line in my book. And the unit vector, V1, is the eigenvector. This gives us the best approximation to our data in one dimension, meaning that that first principal component minimizes the orthogonal distances between that spanning line and the points. So if I project the data onto this direction, I will have the least error one-dimensional approximation of the two-dimensional data. And this is not a regression line. While it may look close when I draw it in two-dimensional situations, there's no target variable in PCA. I am simultaneously trying to represent information there in the height, which is here as H, and weight, W. I'm simultaneously trying to represent the height and weight of participants with just one number. So it's very important that you recognize that in regression, we give preference to our target variable, and we try to find the line that minimizes the vertical distances of the points to the line. Whereas in principal components, we're talking about minimizing the orthogonal distances of each point to the line to give us the best representation of both X and Y. So there's no target variable. I'm not using X1 to predict X2. I want some representation of both of these variables. The second eigenvector of a covariance matrix will point in the direction orthogonal to the first that has the next maximal variance. Now, of course, when we're in two dimensions, I only have one other option for the direction orthogonal to the first. I'm talking about that direction there that's perpendicular. But if you'd like to imagine, just for a minute, a three-dimensional example, if I imagine I have some data that's like dispersed throughout this ellipse, the direction of maximal variance would be this V1 direction. And my next choice is to find the vector V2 that's orthogonal to the first. So being orthogonal to the first means it has to point along this purple plane here. But I want the vector that's on that purple plane that next maximizes the spread of the data. And it looks like in this ellipse, we have some compaction here, and this is the direction of the next maximal variance. And then for the third vector, I'm kind of locked in to the last axis. There's only one more axis that's orthogonal to the first two. And principal components, if we'd like them to, will provide us with a new orthogonal basis where the coordinates of the data points are uncorrelated. So all I've done here is take my V1, my first and second principal components, and I've rotated my picture so that it's, in the traditional view, having a variable along the horizontal axis. And you'll see now this data is uncorrelated. V1 and V2 are two new variables that are completely uncorrelated. And that will always be the case in principal components. But you can see here, just for reference, I still have the height and the weight kind of opaque on this chart, or sorry, transparent on this chart. Each principal component is a linear combination of our original variables because it's just a vector that points in a direction. Okay, so V1 was a direction that points, a vector pointing in a direction, and the direction that it pointed in was 0.7 height plus 0.7 weight. Why is it 0.7? Well, because this is a unit vector, so it was the direction 1, 1, and I've normalized it by dividing by the square root of 2. And V2 pointed in the direction of -1, 1. Now, these entries give us the loadings of each variable onto that principal component. Now, as it turns out, I can actually use these formulas in reverse to think of our original bases, that would be weight and height, as linear combinations of the principal components. But what I really want to get across here is this idea of a biplot. When I show this in 2 dimensions, it's not going to be groundbreaking. In fact, students typically look at this and wonder why I'm even presenting it. I have a reason. When we get to a real biplot where we have multidimensional data projected down into 2 dimensions, along with those original variable vectors, then things get a lot more complicated. But the way that we take information away from a biplot is the same. So hear me out. I have my uncorrelated data plotted on our new axes, V1 and V2. I also have my original variable axes plotted on that same picture. And my claim to you is that as I move in this direction, and you can think about kind of holding a piece of paper perpendicular to this weight axis, and as I move up in this direction, as points become further and further along this direction, their weight increases. And similarly, as I move further and further along this direction, the height increases. So, again, think about a piece of paper moving along this direction perpendicular to it, so that these points here have the largest height and these points here have the largest weight. Now, of course, if I were to rotate this picture back the way it was and give you those same conclusions, you would look at me like, why are you telling me this? Do you think I don't know how to read a graph? And that's great. I want you to say, yes, okay, that conclusion is completely trivial. Because when we move into, like I said, those projected axes, we're going to have to stretch our brains to draw the same conclusion. Now, those variable loadings actually give us a formula to compute the coordinates of our data in the new basis. So for every point, the data I've collected is height and weight. So in order to get their coordinate along V1, I simply take 0.7 times the height plus 0.7 times the weight. Now, there's a big caveat here, that the heights and weights that I've collected, again, I'm thinking of them as centered data to begin with, or standardized data if I'm using correlation PCA. So when I see these formulas, I would take 0.7 times the individual's height minus the mean height, plus 0.7 times the individual's weight minus the mean weight. And we'll get some practice with combining these ideas in just 2 slides. So here's a first set of practice problems and some more practice problems. Again, keep in mind the loadings give you a formula for the coordinate in terms of the centered data. And each of these loadings corresponds to the variables in order.